Okay, so number 9 has h of x times g of x. And the two that you're multiplying together there, the g of x is negative 3x to the 4/3, and h of x is x to the 1/2. So Jacob, if you're multiplying them together, like how'd you start it?
I realized that I did wrong.
Oh.
I had the wrong number.
Oh, that'll make it wrong.
G of X.
So what did you do then, Jacob? Just in case somebody else had the same question.
I did it right. I did it wrong.
Okay, so if you're multiplying them, you have x to the 1/2 times negative 3x to the 4/3. So really this x has a 1 in front, so if we're multiplying the numbers together, 1 and negative 3 remain as negative 3. Looking at the x's, how do you combine the x's? What do you do with those to add what? Yeah, we want to add the exponents together. So we're adding 1/2 and 4/3. But Alex, what would the common denominator be? 6. So 1/2 becomes 3/6. 4/3 is, and when you add those together, you get 11/6. So multiplying the 1 and the negative 3 make the negative 3, and then adding the exponents to get x to the 11/6. So negative 3 and then x to the 11/6. Questions? Alright, so number 13 dealt with a different group of functions. So number 13 says take f of g of x. Bless you. That was 2x plus 3 for the f function, and the g function is 3 over x plus 1. And again, we're using f of g of x. So how do we start one of those problems? Yeah, you go into parentheses. So inside the parentheses is g of x. That's 3 over x plus 1. And then what do you do, Alex? So we're going to take that piece and plug it in for x. So you're not just multiplying the two together, you're literally taking one and replacing it into the other. So it's like using substitution. So we have a 2, and then instead of x, it's whatever's in parentheses. So I'm not writing x, I'm going to write this quantity here, 3 over x plus 1. And then there's still that plus 3. So it still looks like 2x plus 3. It's still in the same form, but we replace the x with whatever g represented in this problem. How do you multiply these together? Eris? So the 2 is really over 1. So 2 times 3 is 6. And then 1 times x plus 1 stays as x plus 1. And then there's the plus 3. This is actually as far as you need to go. So the answer on the back was a little different because the answer continued to get common denominators and work through the problem. We haven't really done anything with common denominators with variables. So if you have this answer, check your page, then you've done the problem correctly. So if you got to this point, then you did work through the problem. So just making sure, though, that that 2 only goes to the top, because that's been the common occurrence that I would see. The 2 does not go to the denominator, because it's not 2 over 2, it's 2 over 1. So any whole number can be written as a fraction over 1. Because they continue to simplify the problem with a process we have not done yet. So it's using common denominators. We'll talk about it in a second. Any questions on 13? Okay, so then looking at the last group, 20 and 22, I think were the two that I've heard. So that group of problems used 3x plus 2, 2x squared, and negative 4 over x plus 3. So number 20 says take h of x minus f of x. So our h of x is the negative 4 over x plus 3. If you're subtracting f of x, remember you're subtracting all of it, so you have to subtract the 3x and the 2. So the only thing you can do with this problem is distribute the negative through. So this negative goes to both pieces because you're subtracting all of f of x. So it would be minus 3x and then minus 2. But there's no other way for you to continue to try and add these together. So I can't like take a negative 4 and add it with the negative 2 because these are really over 1 and this is over x plus 3. So they don't have the same denominator for you to continue to work through the problem. However, you were asked to find the domain for this last group. So what would we have to use to get the domain for number 20? What would affect the domain in a problem that looks like this, Amanda? Right, so wherever you've got a denominator, which is at x plus 3, that can't be 0. So Amanda, x cannot be, right, negative 3, because that's what makes the denominator 0. When you have a domain, whatever makes the denominator 0 or whatever makes your square root negative is not part of the domain. So if this can't be negative 3, that means it would go from negative infinity to negative 3 with parentheses, and then negative 3 to positive infinity. So again, this is your answer right here. Don't do anything else with it. There's no way for you to try and combine those values together. So leave it like this. Make sure you've got both of those negatives carried through. And then the domain was negative infinity to negative 3 and negative 3 to infinity. Questions? The last one, if you look at 22, is g of x divided by f of x. So g of x is 2x squared. F of x is 3x plus 2. Can that be simplified? Can you cancel something out? Reduce something? Remember, if you can't do it to one term, then you can't do it at all. So even though this has an x squared and an x, you can't cancel it out because the 2 doesn't have an x. So this is the simplified answer. So if you can't cancel it from all of the pieces, then you're not allowed to cancel or reduce the problem. So it's the 2x squared on top because that was g of x. F of x is 3x plus 2. So just like the other problem, the denominator is not allowed to equal 0. So this denominator for the domain is still not allowed to equal 0. So you were asked to get the domain for that bottom 6 problems. So what would make the denominator 0? If we have 3x plus 2, what makes the denominator 0? What number? Sean?
Negative 2/3.
Awesome. So negative 2/3 is what x is not allowed to be. Because if we plug that number in, we get a 0 in the bottom of the fraction. So negative infinity to negative 2/3. And then negative 2/3 to positive infinity. I think the common theme is that you want to oversimplify, over-cancel, combine things when you really shouldn't be combining them. So don't cancel that if they don't know how to tax it. Questions? If you could pass that forward then please. I don't need the sheet. I just need your work. You'll turn to page 17 in your chapter 6 packet. We're going to start section 6.4 today on inverse functions.
Socks are so good.
page 17. Probably not, but it is somebody's from one of my 5 classes. So we're going to look at verifying and finding inverses today. Chris, what is an inverse? So if something is an inverse of something else, what does that mean, Morgan? Opposite. So inverse generally means opposite. So in math, Chris, can you name 2 like operations that would be opposite of each other? And no. Let's start. Go back.
That's addition and subtraction.
There we go. So addition and subtraction are inverses, opposites of each other. Chris, the other pair would be
Multiplication
and
and
division, right? Those are also opposites of each other. So an inverse relation, not talking about inverse operations, but an inverse relation happens when we interchange the x and y variables. Because x and y are pretty much opposites of each other. X is independent, y is dependent. So to find an inverse relation, we're going to see if we can interchange those two. So interchange means switch, replace, flip, however you want to look at that. But we're going to be interchanging, switching the x and the y to find an inverse or an opposite relation. An inverse function is when the relation, and a relation is just like a set of numbers, or any equation is a relation, and the inverse are functions. For something to be a function, what has to happen? Talked about this last week. So if something's a function, what does that mean? David? Each input has exactly one output. So we're going to be comparing one equation to another to see if they are inverses of each other, opposites of each other. They have to be functions. So each input has to have one output. When that happens, we can write it in inverse notation as a function. So generally we write functions as f of x. That's a function. So if each input has one output, we say it could be written as f of x. That's the notation we use. Well, inverse functions also kind of look like function notation, but they have a little -1 attached to the f. So we would say f to the -1, or the inverse of f, dealing with the inverse function relating to our original equation, or the original function. So this is inverse notation. When you see this little -1, it doesn't mean that you're supposed to move it to the denominator, because it's not the independent variable, it's the actual function notation. So just to give you a little idea, and an example to look at before we actually work with some equations, if you have the function, I'm just going to get a set of ordered pairs here. So we'll say like 0, 3, 5, -7, another good number, 10, and 2, doesn't matter, there we go. So this is a function. David said each input has exactly one output. Well, my input x's have one output, so this would be a function. A function can just be a set of points, it doesn't have to be a line. How would you find the inverse of that function? How do you think you'd find the inverse? Alex? Make it like 3, 0. And then? And? Yeah, that's all you have to do to find an inverse. So it's literally interchanging, switching, flipping the x and the y values. It's not making one positive and one negative, because that's not really switching x and y. So to find an inverse function, literally you take your ordered pair, you flip it around, and then you have the inverse. So with equations, there's a little process, and it's not really involved. It's stuff you already know how to do. In order to find an inverse that would be in equation format. So the first thing says replace f of x with y. So if my equation starts with f of x, we're going to change f of x to say y. Well, that's pretty easy to do that. The second thing says switch x and y. So literally, we are going to flip-flop x and y, and then solve the equation back for the y variable. So after we switch them, we're going to see if we can get y by itself. The last step is kind of like the first step, just replacing something. It's not really doing anything mathematical. But we're replacing it, saying whatever equation we now found after doing this process is the inverse of our initial equation. So if you look, there's two problems underneath this, just trying to get you used to how to find an inverse. So find the inverse of the equation, y equals 3x minus 5. So I don't even need to do the first step because y is by itself. It's already y equals. So the second step says switch x and y. So literally, you're going to take the y out, switch it to the letter x. And then on the other side, you're taking the x out and switching it with the letter y. By doing this, this will help us get the inverse, or the opposite of what we started with. The opposite of y equals 3x minus 5. So, Zach, how do we solve for y? That's what it says to do after we switch.
Make x 0.
How do you get y by itself? Yes, you do.
Add 5.
Add 5.
Divide by 3.
There you go. Did David tell you that too, or did you get that on your own?
I got it divided by 3.
Oh, good. All right. So add 5, divide by 3, and we get x plus 5 divided by 3. So solve the equation for y, get the variable by itself, and then write it back with the notation showing that you found the inverse from the equation that you started with. So the inverse of f equals x plus 5 divided by 3. So Chris said that multiplication and division were inverses. So we started with multiplication, we now have division. He also said addition and subtraction were inverses. We started with subtraction, and now we have addition. So you can see even from the equations, like they look like they're inverses or opposites of each other. Questions? So look at the second one. F of x equals 1/2 x plus 2. Change f of x to y. Flip your x and y. So those first two steps really don't involve a lot of thought. You're just rewriting numbers. Jacob W., how would we solve for y? So we would get y by itself.
Right, so subtract x
Instead of subtracting x, keep the x and the y where they are. So subtract 2.
Multiply with
Let's take the 2 to the other side first. Subtract 2, and then multiply by 4. Yeah. So you're going to take the 2 to the other side first, take that to the other side, and then multiply by 4. So if I'm multiplying by 1/4, you multiply by its reciprocal, then it'll get rid of the 1/4. What do you multiply by 4 on the left side? Just the x? Or the x and the -2? Jacob? Both, yeah. Whatever you do to one thing, you got to do to all of it. So you would have 4x minus 2, or minus 8, sorry. So the inverse is equal to 4x minus 8. Questions? So finding an inverse is as straightforward as flipping x and y, solving for y, writing it in inverse notation. The other thing that we're going to look at today, besides finding the inverse, is determining if functions are inverses. So instead of finding it, they're going to give you two equations, and you'll be asked to decide if they are inverses of each other. So functions f and g are inverses of each other, provided, so this kind of sounds like a conditional statement from last year, f of g of x, we did this yesterday, that's that composition function, is equal to x. So after we look at f of g of x, it's going to simplify just to the letter x. And means they both have to happen in order for it to be true. G of f of x also has to equal x. So yesterday when we were plugging in the numerical values, if we plugged it in one way and then did it the opposite, in most cases we got different numbers. Our goal this time when we do the one way and then the opposite is just to get down to the letter x. If that happens, then we could say that they're inverses of each other. So this is a good way to check to make sure you didn't make any mistakes when you were finding the inverses. Verify is another way of saying confirm. Prove, which you guys don't like that word, prove. So in a way we're going to do a little algebraic proof to see, verify, confirm that two equations are inverses of each other. So we have f of x equals 3x minus 5. So that's our f of x part. And then it says this is the inverse, and we want to confirm or verify that it is. And it's 1/3 x plus 5/3. So we're going to think of this as our g of x equation right now. That's going to be our g of x. So to verify, it says that we need to take f of g of x. So this is what we did yesterday, those composite or composition functions. Start in the middle, so start with the g of x. That's my inverse, so we're kind of using the inverse as the g function. So that is 1/3 x plus 5/3. What do you do with that equation now that we've replaced g of x with it? Zach?
Plug it into 3x minus 5.
Right, we plug it into 3x minus 5. So we're not multiplying 3x minus 5 by it, we're plugging it into 3x minus 5. So instead of x, we have 1/3 x plus 5/3, and then there's a minus 5. I know there's fractions, but they work out nicely. So if you're multiplying by the number in front, if you distribute that through, Eris, do you know what happens when you have 3 times 1/3? 1. How about 3 times 5/3? 15/3, which is really just 5. And then there's a minus 5. What happens? They cancel, and you just get x, which is what we were supposed to get. F of g of x is supposed to equal x. So we have that one part, we're like halfway there. All you have to do is try the other side, and you do have to do both because they won't always both equal x. So we need to do the opposite to make sure that it also equals x. So we'll start with the 3x minus 5. And just like Zach said for the previous one, you're taking this, plugging it in for x. So you're always plugging it into the x of the other equation. So 1/3 times 3x minus 5, and then plus 5/3. So David, 1/3 times 3 is? How about 1/3 times negative 5? Good. And then plus 5/3. So that's the part right there that cancels out for us. And magically, you get x. So this is a proof. You've just done a little algebraic proof. You've shown that these two are now inverses of each other because they both equal the value of x. They both reduce down to the value of x. Questions? So if you flip the page, there are actually 3 examples here, and I don't think we need to do all 3. So we're just going to look at the middle one. And if you need to use all of this space there because it's a multiple step problem, then you can feel free to do so. But it says to find the inverse of the given function. So we're going to do that part first. And then it wants us to verify our result and the problem we started with to make sure that they are inverses. So the first part, we'll make sure to get the inverse, because I need an inverse in order to verify something. So this becomes y. And then Donnie, what do we do to find an inverse after you make it in y equals?
You make it x equals 2y minus 1.
Good. And then?
And then plus 1 on the other side.
Good.
Divided by 2.
So the inverse, we added 1, so it's x plus 1. And we divided by 2. So here's the inverse. After you find it, it says verify your result and the original equation. So we want to now verify, prove, confirm that we didn't make any mistakes when we found this inverse, and that it should match up with the original equation. When we combine both of those together, they should equal x. So we're going to do that f of g of x and g of f of x. Remember, this is the g function. That's the middle function. So the inverse is also kind of that second function that we're going to use. So g is x plus 1 over 2. We're plugging that in place of x. So 2 and then x plus 1 over 2 and then minus 1. There is a shortcut to simplifying this. Does anybody know what a shortcut would be? David?
You can cancel out the 2's.
You can cancel out the 2's because this is multiplying, dividing. If it's in the denominator, you're really dividing by that number. While the opposite of multiplication and division, they cancel each other out. They're opposites. So you don't even need to distribute that 2 through if you're dividing it by the same number. They just cancel out. So then we have x plus 1 minus 1, which is just x. So there's our one side. We get the x. So anytime you're multiplying and dividing by the same number, they reduce, cancel it out. Don't actually distribute that through. It gives you more work to do. Looking at the other side, we're going to look at f of x in the middle. So 2x minus 1. And plug that in for the x of the new equation we just found. So on the top, we would have 2x minus 1. That's my x. And then the plus 1 divided by 2 was already there. So negative 1 plus 1 cancel. We have 2x divided by 2, which is also x. So questions with finding inverses or verifying inverses. So those are the two things that we looked at doing. So the last part here that we're going to stop at with this little graph. So it wants us to find the inverse of a power function. The power function we're working with is x squared. Anybody remember what the shape of x squared is? David? A parabola. Yeah, remember this is the u. It's a parabola. So if you do a quick mental t-chart, we're just mentally going to graph this. Plug in a 0. 0 squared is 0. So my first point starts at 0. What's this part over here mean where it says x is greater than or equal to 0? What's that mean? Yeah, the numbers that you pick for x have to be greater than 0 or equal to it. So we picked the one that was equal to it. Plug in the number 1, square 1, get a point. Mrs. Kane. Hi. Yes. Okay. Alright. So if we plug in a 1, 1 squared is 1. If we plug in a 2, 2 squared is 4. So if x is 2, 2 squared is 4 for y. And we're only choosing x's that are bigger than or equal to 0 because that's what the problem told us. So instead of having the other side of the parabola, we just have this one piece here. So that would be our graph. The second step says find the inverse. So we've graphed it, the 1/2 of it. Now we want to find the inverse. So if we get the inverse, we switch x and y. How do you get y by itself when it's squared? Square root it, yeah. So if it was cubed, we would cube root it. So now y is by itself and it's equal to the square root of x. So our inverse of x squared is the square root of x. The last part of the problem says graph this inverse. So do another mental t-chart. If you need to make one, write it down, that's fine. But you can just do a mental t-chart. So if you plug a 0 in, the square root of 0 is 0. If you plug a 1 in, the square root of 1 is 1. What would be the next number that we could have that's a perfect square? 4. So 4, the square root of 4 is 2. They should be opposites of each other. 2 squared was 4, so the square root of 4 is 2. So we should be able to flip those ordered pairs. If you connect them, you're connecting it, kind of making like the opposite curve. So an inverse means opposite. My graphs should look opposite of each other as well. They should be opposite curves. So the inverse function worksheet, you're doing just the front of this. And this is the worksheet I'm giving you right now. So only do the front, do not do the back unless you feel compelled that you'd like to do more math work over the weekend. But there's 8 problems on the front where you're finding inverses or verifying inverses. And then I have a composition worksheet to review domain and compositions, and you're doing the back of it. The back of it just says example 1 at the top. So make sure you do the back of the composition worksheet, the front of the inverse worksheet. Anybody interested in doing 1 or 5 from the inverse worksheet for Monday to present to the class? Julia, you have to do 1? And Abby 5? Kyle, I get you on Monday. So the 4 problems, the back of the composite, those 4 problems, the 8 problems on the front of the inverse. No book homework, so don't worry about doing the book homework. Have an awesome weekend.